Lift and coast is a technique used by racing drivers to save fuel, lower brake temperatures, and to a lesser extent, help with tyre life. In this video, we're going to look at the theory behind lift and coast, and also a practical demonstration of lift and coast techniques. The whole idea behind lift and coast is that when we're going around a racetrack, there are certain scenarios, particularly over a race distance, where you need to try and conserve certain quantities on the car. For example, if your brake temperatures are running a little bit hot, a little bit high, you need a way to cool them. If you're running low on fuel or you're looking like you're not going to make it to the full race distance with the amount of fuel you've got, you need a way to save fuel. And the key thing here is that we want to achieve these effects without costing ourselves too much lap time. And this is where lift and coast comes in, because it's quite a lap time efficient means of improving these particular quantities. So if our key objective is to reduce fuel burn on the track, one of the things you want is less time on the throttle, because obviously time on the throttle is equivalent to fuel burn. So if you're pressing the throttle for a longer amount of time at max throttle, you'll burn more fuel. Similarly, if we want to reduce brake temperatures, that's more or less defined by the kinetic energy used in the braking zone. So we want to reduce the kinetic energy used in the braking zone. Given that our lower speed when we enter the corner is more or less fixed, what we need to do is decrease the speed at which we start braking. So with those things in mind, our key objectives here are use the throttle less and brake at a lower speed. And to explain how we'd achieve that with our lift and coast techniques, what I'm going to do at first is assume that we have a car that is frictionless and has no drag. So our driver's going along our straight, he goes along, his speed's increasing, and under normal conditions, he would go, wait until the last possible minute to brake, switch off the accelerator and onto the brake almost instantaneously, and then the speed would drop rapidly to the point that he was then going slow enough to take the corner at the end of the straight. In a lift and coast condition, you play it a little bit differently. You go and you accelerate up, and then what you do is you lift, you get off the throttle early, so we'll lift say about here, and then if we assume the car is frictionless, like I said, our speed will continue along like this, and then you brake at this point here. So you lift off the throttle earlier than where you would normally, and you get on the brakes later than where you would normally, and notably at a lower speed than where you would normally. Of course, in a real world, the car isn't actually frictionless, and in fact on high downforce cars, there's quite a lot of aero drag, which slows you down a lot. So if you would lift at this point, your speed profile actually looks more like that. Now you can see that I've achieved our two main objectives here. I've used the throttle less because I haven't been using the throttle for this whole time frame here, and I've gotten on the brakes at a lower speed. So we're going to get less kinetic energy into the brakes, which means less brake temperature, and we're also going to get less time on throttle, which means less fuel burn. And of course, these particular lifts could be either a partial lift, so partial off throttle, or you could be a full off throttle lift. Now, of course, I've chosen a particular condition here by saying we want to accelerate to the high end of the speed and then lift off the throttle and then let our speed drop. But there are other ways in which you can do this if our key objective is to reduce brake temps and reduce fuel consumption. So let's explore those a little bit and see why they are not the favored approach compared to lift and coast. One approach you could do is you could accelerate less at the start of the straight. So you could go and use less throttle here, come up here, and then you'd have a slower speed by the time you reach here. Now, speed down a straight is effectively area under this curve. And this is why this technique is not a good idea, because we lose time the whole way along here, and then we're still losing time at this point here. So if we want to get the same braking speed as here, and we want to keep it the whole way pinned, it would still look something like this. So we'd have way less speed along the straight. So you can see straight away that using a partial throttle strategy out of a corner is not a good idea. The next approach you can consider is delaying getting on the throttle at the exit of the previous corner. So what we would do is we would instead lift coming out of this corner here, and this would give us more time off throttle, so we wouldn't be burning fuel through here, and then we get on the accelerator. So we spend a little bit of time lifting, and then we more or less would follow our same curved trajectory as here, and we get to here, and our speed is lower. But again, you can see less area under the curve. And this means that overall, in this segment of straight, we are going to be slower than going full throttle at the start of the straight and then just lifting at the end of the straight. The other way to attack it would be to brake earlier. Brake earlier, brake a little bit softer, and then use that technique instead. So what you'd do instead is you'd go and you'd brake at this sort of rate here. So we can see there's two problems with this. One is that our speed at which we start to brake is higher, so we are ending up with a bit more kinetic energy, although our braking does occur over a longer distance, so that aerodynamic drag does help us out a bit with dissipating the kinetic energy. So we're probably a little bit better on our overall braking energy than we were if we were just going straight ahead. But we've lost a huge amount of pace yet again. We are sitting with a much smaller area under this curve, and that is going to make our car slower overall. And from these comparisons, you can see why lift and coast in the traditional sense is the favored way of conserving brake temperatures and fuel. So how much energy can lift and coast actually save when you do it? What's the sort of brake temperature difference you're going to see? Well, brake temperatures are all about heat input and heat output. So when we have a traditional brake drum set up on a race car, what happens is we have cooling air going through the wheel and going through the brake disc, the rotor, and this cooling air takes heat out of the system. Now, a lot of the work that's done by this particular cooling mechanism is done at higher speeds where there's more airflow. However, the straight is such a long thing that we still get a lot of that done by the majority of the straight. And if you were to lift and coast 10% early, you wouldn't take 10% off the overall cooling of the system. In terms of what the heat input into the brake system is, well, that's purely defined by the change in kinetic energy of the car. There is, of course, a component of the deceleration that is caused by aerodynamic forces and friction, like I mentioned earlier, but overall, if we're looking at what our difference is in terms of how much heat input is going to the brakes, we can look at the kinetic energy of the car for a rough comparison on how much difference we're making to the overall heat input into the brake system. Now, if we were to consider the car as just an object, the kinetic energy of an object is defined as a half times the mass of the object times the velocity of the object squared. So the important thing to note is that when we're looking at an object of fixed mass, the kinetic energy scales with the velocity squared. However, pace of a car around a track in terms of lap time is proportional to the actual velocity. So we have pace being proportional to a linear component, which is velocity, and then we have the kinetic energy being proportional to a parabolic component, which is the velocity squared. Now, if we were to say that our previous speed was 300 k's an hour up there, and we were to say that we assume a frictionless car because I want to neglect air resistance, etc., because that complicates the equations quite a lot, and say that our lift and coast gets us to 275 k's an hour there, that is a 19% difference in kinetic energy between those 2 points. Of course, if we just look at the linear ratio between those two speeds, it's only a 9% difference in speed. So you can see that I've lost 9% in my peak speed here for a 19% change in my overall kinetic energy, which means my heat input into my brake system is going down by 19%, assuming lossless, but my pace has only dropped off by 9%. And it's worth noting that this is only the pace in the final portion of the straight, which you only spend a very small amount of time here because you're traveling so fast. So overall, I'm not losing a whole lot of pace, but I am gaining a lot back in terms of my heat input. So that's a bit of the theory behind lift and coast, but let's have a bit of a look at a practical demonstration of some of the lift and coast techniques that I've presented here. So what I've got here is something very similar to an F1 car running around Monza in Assetto Corsa. Now, I am the one driving it, and of course that comes with a disclaimer that I am not a professional driver by any standard, and there are some inconsistencies in my lap as a result. To try and make myself a little bit more consistent for this video, I've turned on a little bit of traction control and also turned on the ABS so I can maximize my braking. Now, there's a lot of data going on screen, but the few areas that we're going to look at are going to be the performance delta up in the top left-hand corner, which basically tells me if I'm going faster or slower than my best lap. Then in the bottom right corner, I've got my pedal traces, so you can see how much throttle or brake I'm applying at any given point. And then over on my suspension tab, you'll note here that I have my tire temperatures too. We'll take a brief look at these as well. And of course, at the bottom, you can see my gear, speed, and revs. Now, I've done some laps with a few different styles, but the main one that we're going to talk about is going to be this full attack style lap where I switch straight onto the brakes versus a lift and coast style lap that is presented here. So for this comparison, I've got the log data of my lift and coast style lap in blue and my log data of my normal lap in red. The normal lap onboard is on the left-hand side of the screen and the lift and coast onboard is on the right-hand side of the screen. On the log data, we have a speed trace first, so that's speed over distance. Then below it, we have a throttle trace, so you can see when I lift. And then below that, we have our time delta trace. So this is whether or not I'm faster or slower than my best lap. Now, before we get into playing the video of the lap, I want you to observe the difference in the shape of the two different traces. You'll notice in the lift and coast style lap that I have that taper off in speed. Now, I've tried to lift somewhere between 75 to 100 meters ahead of my braking zone, and you can see that taper off in the speed slope. As a result, I'm about 40 k's an hour slower when I hit the brakes. So we're talking 300 k's an hour versus 260 k's an hour. So significantly less kinetic energy when I get on the brakes. However, my cornering speeds are pretty much the same. We'll try and ignore the latter half of the lap because I obviously was driving a little bit inconsistently when you look at the cornering speeds in that section. So in the first instance, we're coming down the straights, and you'll notice that as we enter the braking zone, on one side of the screen, I lift. And the other one, I wait and then slam the brakes at the end. Now, when you see that, you'll see that the end cornering speed is pretty much the same. You'll note that in the lift and coast condition for this particular lap, I broke a little bit earlier than I should have. I do find it much harder to judge braking points when lifting and coasting versus keeping flat to the end, but obviously a professional driver wouldn't struggle with this. Overall, you'll see that the delta time between these two conditions in terms of the actual delta we're losing in the lift and coast is only a couple of tenths. We're not losing very much. In fact, even with my much earlier braking, I only lost about half a second through this cornering sequence. Another thing to note is that the tire temperatures are different between these two cases. Much like the brakes, the tires will be heated up by the kinetic energy being dissipated as you try to slow the car down. If you have a look at before the braking effort has started, the tire temperatures in both of these cases are about the same. However, by the end of the braking zone, the difference between the lift and coast condition and the max attack condition is 3 to 4 degrees in surface temperatures, which is not a small amount, all things considered. So we can see those lift and coast effects really at work. Now for the next cornering sequence, I got my braking point much better, keeping it almost identical between the lift and coast and the non-lift and coast scenario. In this particular case, my lift and coasting has cost me about 1.1 tenths when I look at the actual data numbers. When you think about how short a time frame change that is, and the fact that I've managed to save a lot of temperature and a little bit of fuel in the process with barely any sacrifice in time, you can see why this is a useful tactic. Let's take a look at some of those alternative methods of achieving the same effect that I mentioned earlier on in the video. First up, we're going to have a look at me going to not full throttle coming out of the corner exit. You'll see that coming into this cornering sequence, I was a little bit faster. By the end of the cornering sequence, I'm about 2.5 tenths up, but then I decide to only use about sort of 75–80% throttle, and you'll see that the speed trace has offset with a gentler slope. Now, what does this mean? Well, instead of being 2.5 tenths up, by the end of the straight, I'm just a bit over 3 tenths down. And you'll also notice that because this straight was long enough, I didn't end up taking any speed off. I'm in fact at the same speed by the end of the straight, more or less, because we're drag limited. So all I've done is just save a little bit of fuel, but haven't helped my brake or tire temperatures. But I've lost half a second in time. So you can see that this is not a very good approach. And finally, as a bit of an investigation into a catastrophic approach, we're going to try the approach of me not putting on the throttle for the same sort of time that I'd be doing my lift and coast. So I go through this cornering sequence, and again, I'm 2 tenths up at the start of it. And then what I do is I do a pause. I don't apply my throttle, and then I apply the throttle, and you can see it's the same sort of speed curve but offset, but the time loss is catastrophic. Just on this straight alone, I lose about 1.7 seconds versus where I could have been. I then do the same approach out of the second chicane, and you'll see that I'm now up to almost 3 seconds behind on my delta. And as per the previous partial throttle approach, my end of straight speed is very similar, so I'm not helping tire or brake temperatures much at all. All I've done is save a bit of fuel at the cost of a huge amount of lap time. And that's a really good demonstration as to why lift and coast at the top end of the speed range at the end of the straight is great on saving fuel and temps without costing a whole lot of lap time. Well, that's all for this video explanation on lift and coast. Hopefully you enjoyed this video. If you liked it, don't forget to hit that like button and subscribe to my channel for more content like this. Leave a comment below on what video you'd like to see from me next, and hopefully I'll see you next time.